Is it on? YouTube is on?
Yeah.
Okay. Thanks. Okay, welcome everyone. Happy to have Ashok working Makkuva in between UIUC and EPFL. So he's mentioning he just finished his PhD. His postdoc. So there's a lot of interest in the intersection of machine learning, information theory, coding theory. So we'll learn about that intersection today. Some of that. Ashok.
Thank you for the introduction. Hi everyone, I am Ashok. So today I will be talking about a recent work titled KO codes. So this is joint work with collaborators Shyam, Vahid, Hesam, Seung, and Pramod. So the main outline.
See the focus
on the
click.
The main outline for today's talk, I will briefly start with what's the motivation behind why we want to design codes using today. So I'll start with the motivation behind, or the main motivation behind why we want to design codes using machine learning. So then I will introduce the framework for learning codes, and then the bulk of the talk for today would be, as the title says, about the KO codes, which are a new class of codes designed by neural networks. And towards the end, I will give some interesting directions along this space in the theme of designing codes. So let's get started. So yeah, we all live in the age of information where no matter how far we are able to communicate and talk to each other at breathtaking speeds. And in case you ever wondered how did we reach here, right? There's a lot of the many strides that we took to get here. So, but in the next few slides, I will give you a brief. You take it on a brief stroll down the history lane. So, let's say like once upon a time, the Alice and Bob were good friends, and unfortunately they got separated, and they wanted to stay in touch. So, what could they have done? Well, if it was maybe 3000 BC, all they could have done is use maybe messenger pigeons. That's the only option they had. And if they waited for a few more centuries, maybe they could have tried the first courier service in 500 BC. And coming to the modern age, maybe if it's early 19th century, they could have tried telegraphy. If not, maybe a few decades later, maybe a telephone, right? And things got quite changed after the turn of 20th century, where now they could have used wireless telegraphy if it was like even over longer distances. And few decades later, world's first cellular phone appeared. Now they can talk wherever they are, like even over a much broader range of distances. And fast forward and coming to the modern century, the age of smartphones and internet, now they can talk and like have Twitter wars every day, right? So if you look at this brief odyssey between starting with the age of messenger pigeons to the top, there's a lot of monumental breakthroughs that happened that led us here. And of course, like I won't be able to go through about all of them, but one important particular event that happened in 48 that completely changed the landscape of communication is, this you can guess, thanks to Shannon, there was through his breakthrough work, so for the first time gave the mathematical way to look at communication, and through the birth of this paper gave birth to the field of information theory. And there are many like seminal contributions coming from the single paper itself, but one particular thing today I want to focus is on the notion of codes. So here, throughout the talk, I'll be focusing on this end-to-end communications, point-to-point communication setting. The two users, Alice and Bob, and they want to, let's say, communicate a message. So there's an encoder that tries to, encode this message into a longer code word, so that even in the presence of channel, the noisy channel, the decoder receives, let's say, a corrupted code word, and it tries to estimate this message m-hand. Right. So this is the framework for the point-to-point communication. And throughout the talk, when I mean a code, by code I mean this pair of encoder and decoder together. Right. And so this is the parlance I would be using throughout the talk. And so the fundamental goal of wireless communication is to, of course, design a good code so that communication is reliable even in the presence of noise. Right, so this is the classical point-to-point communication setting. And so, yeah, study of it's a very widely studied topic, and like there's a lot of history. And for coming back again, here there's a channel, right? So for a lot of theoretical and practical reasons, classically this additive wide Gaussian noise AWGN channel has been like the golden benchmark standard to evaluate different codes. And you can clearly measure how good a code is, right? You can measure the bit error rate or the block error rate. You can precisely mathematically measure that, can give you a way to evaluate how good a code is. And so it's mathematically a well-defined problem, right? So everything is model is very well defined. But the main challenge here is that the space of codes is just like too large. For example, suppose you were to design a rate half code, let's say, over 100 information bits. So the task is to design 2 to the 100 code words, right? Case 100, and each of them live in a 200 dimension space. So you can see, like, even if you were to brute force search over the entire space, it's just not possible. You can't even fit it on a any device, right? It's just like just challenges, like it's quite complicated, like this astronomically huge search space. So this is a challenging problem, and the problems, like the study of problems associated with this spans like several research communities, and it's a very like a established field. And so if you look at like some of the landmark codes that have been developed across the classical AWGN channel I was talking about, so starting with the very first Hamming codes in 50, there have been a number of landmark codes like BCH, Convolutional, Turbo, LDPC and Polar. So there's a reason why I called them landmark codes, is that because the impact they have had on humanity issues, they have been part of like almost all the global communication standards and like many data storage and many other applications. So there's a reason why these are that popular. And just to put it in another perspective, every mobile phone that has ever been designed used one of these codes. So these codes are like that, have that much impact. And at the same time, as you might have noticed, designing of this course is not easy. As you can see, there's almost like a decade gap between almost every other code. That in some sense conveys it's a very challenging task, right? It's like mostly driven by human ingenuity. And so that's evident in the gap between discovery, the timeline and the discovery of codes. So one of the fundamental motivation for us is, can you somehow so given that these codes are like, discovery of them is nothing short of a human eureka moment, given the impact they had. So the main goal for us is, can we somehow automate the discovery of these codes? Okay, so that's the main fundamental motivation for us behind this work. Okay, so the goal sounds good, but also it's quite ambitious. But how do we do it, right? So how do we do it? We are thanks to deep learning, we are also amidst another technological revolution where we are able to achieve breathtaking success in a variety of fields like computer vision, natural and speech processing, and we have seen many tremendous success stories. And if you were to just look at, this is a brief summary of the success so far. If you were to just a rough overview, is that it can be broadly classified into two regimes. On one hand, we have something like a model deficiency, where suppose there is no underlying model that can explain the relation. For example, think of it as an image classification, right? You don't know what makes an image cat or what makes an image dog. If you don't have a clear mathematical model, we have seen like the success of deep learning, in learning some models, like for example, AlexNet, ResNet, the names you might have heard, that have been able to do very impressive classification. So that's one regime, that of model deficiency, where you don't know the underlying mathematical model. And the other regime, which is equally interesting, is that of algorithmic deficiency. So here you have a very clear, well-defined model. So think of as a game playing, right? Take chess and Go. Here, the rules are very well defined. Like mathematically, it's a well-defined problem. The notion of winning, losing, all the every step is mathematically well defined. But the challenge here is that the space of algorithm is very huge. Like here, the algorithm is the game playing strategy, right? What moves do you make based on the board configuration? What steps do you take? It's just like astronomically huge. So that's just like too big. And even in this regime, it sounds very challenging, right? Even in this regime, we have seen very impressive success of deep learning engines like AlphaGo and AlphaZero and like the many later that were able to achieve very impressive results. And if you think about it, even the problem of designing codes falls under this regime, as I was talking before, right? There's a very clear mathematical model, and the goal is to design an algorithm. Again, the space is very big, and so that's where the notion of the problem of point-to-point communication fits in. And yeah, coming back again, so this is like where the two regimes where deep learning has been like widely successful, and in like especially in the context of like these games where the space of algorithms just too huge, we are seeing like probably arguably the breakthrough of the century, the success of these engines, where if you can design, you are able to design much clever algorithms that can outsmart like the best human players. And so this more than the result, they just showed that if you can combine some intellectual ideas with the engineering, you can achieve results that are probably at that point were thought to be like unreachable to machines. So in the same spirit, inspired by that, our main goal is to, can you somehow capitalize on these tools to discover new codes and possibly discover much more broader class of codes that can outperform the existing set of code. So this is the main goal behind the work. And to put it in other words, so this the timeline we saw right earlier, like starting with Hamming until Polar, we have seen many impressive set of codes. So I deliberately put this here. So given that the time is like you see almost a decade gap, and given that the time is ripe for another invention, can we somehow fill that spot with the next set of codes that are designed by neural networks, and can you progress on this timeline automatically with the help of this engine? So that's the main goal behind this. And there's again that's the main goal, but there's also a dual agenda behind it. So the agenda is the following. So on one hand, so this gives us a new set of tools to study the classical problems, right? The point of like designing codes is like a long-standing field, like from 50s onwards, and so this gives us a new angle to design codes and new tools to discover code. So there, of course, there's a lot of practical value, as we were saying before. On the other hand, this is equally interesting. Is this gives us a a different kind of lens to understand deep learning, which is kind of like a black box, right? So this can the argument is that this can give us a bit more mathematically structured way to look at this, because if you think of this point-to-point communication model, everything is mathematically well defined, and you can tune any knob you want in this model, and you have a clear handle on each and every aspect of this model, so that that can in turn act as like a good lens to understand the deep learning methods, which is the understanding. This is like a wide open thing, right? Many people are studying from various angles, some from signal processing, some from computer vision. Mostly it's, I think, dominated from observations from computer vision and natural language processing, given the applications. So the argument here is, if we but in the settings there, the mathematical models are not that obvious, right? You don't know, you can't even explain the data of images, right? Like what's the model behind it, and there's a lot of some mathematical gaps in those regimes. But here at least it's mathematically very clean setting. So can we use these frameworks to understand deep learning methods and get a good understanding behind this? So that's the other agenda behind why we are doing this. Okay, so again, coming back to the framework of learning a code. So this is again the point-to-point communication setting. There's an encoder decoder channel. So the message, it's a block, right? Binary block. Block length k. You can think of k as like 10 or something. So there's a message, and decoder decodes the message. So by learning a new code, I mean you want to make the encoder and decoder parameterize them as some learnable functions, some suitable class of functions that you like, maybe linear class of functions or some non-linear class of functions that you know of. So you want to parameterize them so that you can learn them. And in case you're wondering how do we learn them, so for learning you can use some end-to-end loss function frameworks. For example, so this is just a binary message block, right? So in the end, let's say m hat is like a soft probabilities of each bit being 0 or 1. So you can use any standard technique, something like cross entropy loss, which is nothing but log likelihood. It's a negative log likelihood. So, and the goal is to minimize this loss. Basically, you want to ensure that your decoded message is as close to M as possible. So you can write an end-to-end loss function. And so this is what I mean by learning a code, the framework for learning a code. And you might notice this looks very similar, almost similar to autoencoder, right? Just the main difference between autoencoder and here is just the order of dimensionalities is switched. In this case, the code word is of longer length compared to the message because you're trying to add redundancy, so you're blowing up the dimension. And yeah, in autoencoder it's the other way around. So this is the framework for learning a code. And
so what is cross entropy? The KL divergence? Or?
Yeah, it's just like the negative log likelihood loss only. If M hat denotes like the probability, right? Given Y, the cross entropy loss is something like this is just a negative log likelihood. If M is the bit is 1, the probability is M hat, right?
So these are long vectors, no?
So
K length.
Right. So this M is okay. Let's say Mi. This is for I. Let's say there are 10 coordinates, right? This you write it for each coordinate and you add it. This is something you can think of it as a proxy for bit error rate. So actual bit error rate is like summation I. Probably looking for a block code. True, but okay, I will get to that. Training on block error rate is hard because too many classes, right? So that's why we are training on bit error rate. Basically, this you can think of it as a.
So it's summation Mi hat not equal to Mi, right?
No. This is a bit error rate. Right? This is the definition of bit error rate.
Yeah, but there's an Mi in a second. Mi hat not equal to Mi.
Yeah. This is the definition of bit error rate. Ideally, let's say there's no block error rate. We only care about bit error rate, let's say. Good. We say code is good if bit error rate is as low as possible, right? This is what you want. But you cannot directly train on this because this is like, what do you say? This you can write it as, let's say expectation. This is summation over indicator, right? Okay, I hope it's not blocking.
It's blocking for some people.
Okay, this I just wrote it as expectation of indicator. Okay, let me write it here. Indicator Mi hat not equals to Mi.
It's essentially the clear divergence because the other thing that you have to add is that does not depend upon Mi.
Right.
What is MI?
Mi hat is the estimate.
Oh, okay.
Estimate.
You're saying it's probability of MI equal to 1 condition.
This is just a definition. I'm denoting what Mi hat is. Mi hat is a probability because you'll estimate probabilities always. I'm not directly estimating my bits. Yeah, just think I send bits here, but in the decoder I estimate the probabilities because I want to train it.
Okay.
Of course you can estimate the bit directly, in which case there's a much more easier way to do it. You estimate the bit and you write a mean square loss. That's probably a cleaner way. I just choose
MI hat is the probability that I get bit output is
1.
So you do this learning for each channel realization, or you have to learn the channel as well?
That is a good question. I will touch upon it. For now, throughout the talk, you can think it is an AWGN channel.
With a given sigma that you know.
AWGN. So AWGN. So this is if X is your code word. So if X is your code word.
But there are these two red and green buttons you can on the
board.
Okay,
So this is done. This is Gaussian 0 sigma square in, let's say. The Y you get is X plus Z.
So that is not a bit string.
This is a block. IID Gaussian, so you add noise to the code word. X is my code word. So this is my code word that comes out of encoder. This is my channel.
The channel is analog.
Channel, yeah, you can think of it. It's analog. Yeah. It's all plus minus ones. There are no, I mean, 0 ones for the purpose of the talk, but in reality, it's plus minus ones. So encoder output is X, the plus minus 1 code word, and the channel adds a Gaussian noise, just 82 Gaussian noise, because these are real values. It's a BPS, because there's like plus minus ones, and the Y I get is like X plus Z. This is my channel. This is what I mean by AWGN. And so wait for this one.
So it's basically sum of KL divergence for marginals, right? For the for each.
Yeah.
So even if you get that to be perfect, it doesn't mean that you're actually transmitting that n hat is actually same distribution as n, right? Because these are marginals that you're fitting perfectly.
I mean, we just need to estimate the. Of course, okay. In an ideal scenario, like there's some fundamental, like even the best code, right? You can estimate the probability only. You're estimating the probabilities.
Yeah.
Like for a given code, you estimate the probabilities.
Yeah.
Right.
Yeah.
And the point is, so this MI hat is a function of this encoder and decoder. Now the goal is, can you tweak these encoders and decoders so that you are minimizing this loss, or equivalently you are maximizing the likelihood as much as possible?
I understand that, but I'm saying that even if you do very well on this benchmark, it doesn't mean that you're actually transforming that M is equal to M hat on most cases or something. It could just be completely different. No?
So when you mean M is same as M hat, like
I mean,
M hat's a probability, so you can think, okay, you just take the sign of that. That's your. So, see, M is just 0 or 1. Now I have the probability of my confidence for bit being 1, confidence is 0.9. So the other confidence point. So I will estimate my bit as 1, right? That's
what I'm saying is that you have a distribution of this Boolean hypercube here. And there you're only looking at the marginals, no?
Here?
Yeah.
For training, yes. For training, yes.
Yes.
For training, yes.
Okay.
Yes, at the end of, okay. In an ideal setting, yes, we care about the block error rate.
Yeah.
You want to recover the entire block,
Yeah.
but that's not easy to train. It's not possible. This is like a proxy.
Yeah.
I will touch. This is a very good question. I will, when I show the plots, I will say what happens. What happens is, even if you train on bit error rate, luckily in our case, block error rate also improves. Generally, it doesn't happen, but in our case, it happened. So, for now, you can think of it as we're using bit error rate as a proxy because we can't train on block error rate directly because there were too many classes. I think there is number of.
So this quantity, what is the optimal? Like if MI hat is equal to M, does it become 0?
This is the KL divergence plus the entropy.
Yeah. This is nothing but the KL divergence. This is between the
plus the entropy.
The true distribution of message block and the P hat M.
And then you have to add a term which depends only upon n, not on m.
Yeah, this is the your theta. Theta, if you call theta encoder and decoder.
Sure, theta is a random quantity which will depend on. Okay, sure, parameter.
PM is the input. This is a Boolean this is a uniform on Boolean hypercube. This is the PM. Ideally, this is what you're supposed to do. Ideally, but this is intractable because this would involve summation across all the message blocks, which is 2 to the k. You can't even write the loss function.
Okay.
So what we are doing is
bitwise,
and we are summing we are doing the bitwise scale divergence
and
summing across it.
Even that too, in the best case scenario should be 0. Right? I mean, if MI hat distribution is the right,
assuming we have theta and like the thing is the following, right?
Okay.
I didn't say where theta is.
But then again, as Hari was pointing out, these are just difference between the marginals that you are looking at. You shouldn't be looking at the joint distribution.
So that's what, like, coming back to the previous. Ideally, this is what this star is like the ideal thing that I want, but this is just too hard because if you expand this, right, KL divergence is summation across all the blocks.
No, but if your input distribution is uniform, then the output, a given network in all this output uniform distribution, the KL divergence will be uniform.
That's not obvious, right? it's supposed to learn it. And okay, but that's the second thing. Yeah, that's the second thing. But the first thing is you can't even write this loss function. That's what I'm saying. Because k divergence will involve summation across all messages in 0, 1 k. Let's say if k is even like something like 20 or 30, you can't even write the full loss function, and you cannot even simulate it basically. So that's why it's just like a proxy. This is the yeah. So as a proxy, we do summation across I, KL between ith bit, again the ith bit as a function of theta, minimize for theta. So this is the loss function that we care about. This is exactly same as this cross entropy thing. Because I mean PMI is like Bernoulli plus minus 1 half, right? So that like, if it's 1, its probability is MI had both are. Okay, yeah. Thanks for the questions, by the way. And this is what I mean by learning a code. This is the framework, and I mean this is not something we introduced. This is well known and like there from quite a while ago. So this is learning a code. So you want to design this parametric class of functions so that you minimize this loss function. Or just think of like. I mean, this is like mathematically being pedantic. Just think of the other simpler way is let's say you're directly estimating the bits and they have a mean square loss. That's it. Mean square is much more simpler, right? I mean, it works for both the losses. So if it helps, you can think of it as a mean square loss. In which case, you are just estimating it to the nearest, rounding it to the nearest thing. So that's the goal. And this is before jumping it into directly because it's a bit more challenging. Let me consider a simpler problem, which is of learning to decode. So here you fix the encoder, and any favorite encoders that be like Polar codes, Reed-Muller codes, convolutional codes, and the goal is to design again a decoder. The task is again the same, right? You have to estimate MNAT so that it has close to MS. So this is the task. So in this, like there's a lot of literature, and like I think as we are speaking, 4 or 5 papers are being uploaded on archive thing. So they are like it's just very widely active. There are a lot of papers. There's a mailing list for HDPC or something like that. Every day I get 10 papers in this thread. So there's a lot of HDPC, I think. Identity. I think some. I don't know full form, but I guess P refers to paper somewhere. I think.
Oh,
Probably. I think.
You don't want to learn for a particular noise SNR. Like you probably want to. You don't want to learn a new code for every.
Okay, that's a very good question. Again, I will touch upon it. So the two things people asked so far is channel. What channel and SNR, right? The sigma basically in this. So I will touch upon both of this. I will. So I mean, as I was saying, there's a lot many papers being written on this, but I will not go into all of this. Of course, I will just give a brief summary of what's happening in this. So in this, what's known is that if you fix the encoder and if you have to parameterize your decoder smartly. For example, in the case of convolutional codes, you know that the optimal algorithm is like Viterbi, right? Which you can think of, which is of course an instance of dynamic programming. And if you think about it, dynamic programming involves like what? A forward recursion and a backward recursion. So there's a lot of recurrence, sequential aspect to it. So if you choose architectures that respect this structure, and the natural fit is something called recurrent neural networks, RNNs. And it turns out that if you, this is like the first order decision you make. If you parameterize your architectures using these RNNs, and on top of that, use some like clever training tricks, people observe that you can learn the algorithm. I'm not saying you can just match like for some specific block length or something. You can learn actually the Viterbi algorithm. Suppose even if you learned it for length 40 and you can test it for length 40,000, it still works. So
but that is all because there are only finitely many parameters in the DP equation.
Sorry, finitely.
So the DP equation is Viterbi is the HMM thing. So it's a finite term reference, the DP equation.
Right, but the thing is you're training it for a specific code. like let's say 40, like if, let's say your k is 40, the rate is half or whatever.
But the different neural network itself has been parameterized as the same number of parameters.
No, it's not. Only this is only at the philosophical level, or not philosophical, like the first order level that I'm using RNNs because I'm inspired by the architecture. But apart from that, I'm not using anything from the dynamic programming. I'm not even looking at dynamic programming outputs. I will just try and using, so the beautiful thing is I will just try and using this end-to-end loss.
Is it just that if I take any kind of like ordering as a time series, the RNN should probably learn it, right? Because
So very good question. So in principle, an RNN can always represent a dynamic programming, but that doesn't mean that it will never learn. So that's the hard part. I mean, in principle, RNN can approximate any function, right?
But that is not depth, but here, so that's what.
Right. So when you want to learn it, all these factors come into play, like the loss landscape, the training regime, the number of parameters, all these things come into play. And so that's why it's a bit fascinating that you can learn actually the algorithm, like not just specific output mapping and all. And you cannot even show all the inputs in some cases, right? Because even if k is like 20, you cannot show 2 to the 20 message or you can train it on. So that's the impressive thing people found in this case of convolutional codes. And similarly for turbo codes and all, you can learn some, these are classical algorithms, right? This is their Reed-Muller and Polar code. So this is what is known so far in terms of decoders. And there's a lot of other stuff happening to cut down on complexities of the existing decoders and all. That's not the focus of today's talks. I will not cover, but if anyone is interested, there's a lot of stuff going on. So again, coming back, as I was saying, our goal is to learn both the encoder and decoder, right? So this is now, as you can imagine, this is a bit more challenging because it's not completely trivial how to do it. And so this is what we want to do: design both the encoder and decoder. So how do we do it? So as this is a natural thing, is in order to approach any problem, you need some guidance or some structure in your problem that you can capitalize on. So in this case, the obvious thing that you can look up to is the code structure. So what do you mean by code structure? For example, if a parameterized encoder has like linear and binary, okay, you can, if you parameterize properly, you can recover all the classical codes, right? Because there's a well-defined each code has a well-defined encoding function and decoding function. By encoder, I mean the mapping function. Okay, I'm not the code book. It's just mapping that gives you a rule. Given a message block, I will output a code block. That's my mapping function. That's what I mean by encoder. Decoder is also likewise. So yeah, if I parameterize them by linear and binary, I will recover my classical codes. But if someone gives you the freedom, right, like you're not restricted in this world anymore. Discover even much more broader class of codes like nonlinear and real value. Discover as wide the code as possible. So an obvious choice, like given the hype we are living in, is the neural networks, like the notion of the standard functions that you can use to parameterize them. But just because you have these tools doesn't mean that it will work. And so the first thing one can try is replace both encoder and decoder by like standard fully connected neural networks, like right off the shelf. Just import PyTorch and just one line, right? So you can do that. But what people observed is that if you just use off-the-shelf neural networks, they work much worse than even like a very trivial scheme like a repetition code. So this is widely known. And so this is to drive home the point that just because you have neural network doesn't mean that life is all rosy after that. You still need a lot of structure on top of using neural networks, if you want to discover something non-trivial. So how do we impose structure on top of neural networks? There could be several ways, definitely, but the one principle that we follow.
So one question. So why are you actually going for this nonlinear networks?
Sorry?
We know that linear networks are secret. So why for AWGN channel that you are considering? So neural network is essentially giving you a nonlinear network, right? It's a nonlinear mapping. So
achieve capacity, but most of the results are like asymptotic, right?
But let's say LDPC is a practical code, right?
Okay. So for that, the answer is like twofold. One is like the first reason is it's more like a scientific curiosity, as in like true. I'm not saying existing codes are bad. Like many of these codes are like optimal and like landmark code. But are these the only codes that are good? Can there be much richer structures that we haven't even encountered upon? That's like more like a scientific pursuit of what else? It could be possible that there's nothing better out there, in which case which is okay, because we tried and maybe in some sense these are very good, so there's nothing better. In which case the answer could be turned out to be that, or if not, we could even end up discovering much broader richer structures. It's enough in that, like it's more like scientific spirit that like
Fair.
Okay. So yeah, I was saying we need a structure, but how do you impose structure? So for that, we use this natural idea, which is, we know the existing codes are good, right? Like they're good for a reason, right? They have many good properties. So the idea is to, can we somehow capitalize on the existing codes and derive some inspiration from these codes to design our nonlinear codes. So, okay, so this is the idea, but how do we do it? And okay, the obvious question is, of course, like how do we do it and what class of codes do you want to look at? So for this, the first question, like how do we use the existing codes? So for this, we use this classic well-known principle. This is just technical jargon. The idea is just, if you know that some code is good, existing encoder, and you want to use like some neural, any neural network based architectures, the idea is just add something on top of existing encoder. That's all this is, this flow diagram is saying. If you know some code is good, use it and add some neural network on top of it. So that's what it's called, neural augmentation.
Add is like concatenation or?
It can mean in several ways. This is just like English add only. Use something on top of existing things. So that's like the idea. And so this is the principle that we follow, and so that's the how, that addresses the how part. And the next, of course, the obvious question is, which is even more important, is what class of codes do you want to look at? Because that's where the structure comes. Sorry, that's where your structure comes from. And for that, so this
yes. I have a question. So can you just go back to the previous slide?
This one?
Yeah. For this, let's say this is a very specific question, but let's take polar codes, for example, right?
Right.
So, like for every channel, right? You will have some sort of the encoder will basically be different. So, what exactly does it mean when you say put a neural network on top of the encoder? You will, like, for every channel, will you learn a different encoder? Because that's clearly not efficient in any sense, right?
So very good question. So I will exactly talk about that in few more slides. But the answer to the main answer is that true. I mean, while it's true that the actual code is different for different channels, but the structure won't change, right?
No, what is this structure? This is precisely what I'm not getting, because I mean, I'll make my question more specific. Let's take polar codes. Okay, so even for polar codes are not actually efficient. The decoding is efficient, but the encoding is not efficient, because some oracle has to come and tell you which bit positions are good in some sense. Okay, I'm not going to go into detail about that. The polar codes are non-uniformly efficient, but even if somebody tells you that bit pattern is different.
Okay, let's do one. So I will touch upon exactly Reed-Muller and Polar just in few more slides. Okay, and
Yeah.
hello.
Maybe we can continue.
Sorry, I think you got cut.
No. I was.
So I was saying that in just in 10 more slides or something, I will exactly almost address this question only.
Sure.
Then we can again discuss that. So yeah, as I was saying before, we should know how we want to use the existing structure, and the second important thing is what codes do you want to use. So for that, this is I was saying it's a brief taxonomy. Sorry, a taxonomy of codes. Like on one hand, you have sequential, like convolutional turbo. On the other hand, you have the graph-based LDPC, and there are algebraic codes. And so, in the context of sequential codes, people already observed that if you can use some right architectures, you can discover nonlinear codes that can even outperform the classical convolutional and turbo codes. But this is mostly like this sequential codes come into play at longer block lengths. And for this work, we want to mostly focus on short to medium block lengths. Like short to medium, I mean like some 10s to 100s, let's say 100, 256, 512. Like max speed write is 512. Short is like anything like 10, 16, 32. So in this code, in this regimes, we know that algebraic codes are very good. In particular, we'll focus on Reed-Muller and Polar codes. And why, you might be wondering why these two specific class of codes. For that, I will just give a brief intro about what these codes are. This is like Reed-Muller 101. So these are classical, this is given by Muller in 54, and shortly Reed came up with an efficient decoding algorithm named after these two. And I mean, they have like a very great theoretical interest from decades, and especially they're very popular in TCS community because they like many wonderful properties they have. And again, there has been a renewed interest in these codes because of their close connection to Polar codes, which got famous recently. And very recently, like last November, they were proven to be achieving capacity for certain class of channels under the beta result. So it's a very recent result. And on the other hand, Polar codes, they don't need introduction, they're already famous. So Arikan came up in 2009, and one of the first codes to proven capacity for a wide class of channels with an explicit construction, encoding and decoding, efficient both. And again, there's a renewed interest because of their inclusion in certain standards of 5G. So, okay, these are like individually Reed-Muller and Polar, what they are, but what ties them together? So it's quite interestingly, they have a lot of common structure. And the structure is what I wrote here. It's called Kronecker Operation, the Plotkin transform. I will explain what that means. And this structure ties them together. And that's one of the main reasons why we targeted these two class of codes. This gives us a unique launch to look at these two codes in a single shot thing. And so what exactly is this Kronecker operation on Plotkin transform? So what I mean by that is the following. So here you see a complete binary tree. Okay, this is an encoding tree for both of these codes, or a computational graph. So at the leaves, you see some message bits, right? Suppose you want to transmit two message bits. In this case, the message bits are 1 and 0. They are being put here. So these boxes you see, these are called frozen leaves. They're always fixed to 0. You'll always send 0 at those locations, no matter what. Okay. Let's say these locations are someone told you, and these locations are fixed, and you want to send a message bits, you send them at these two positions, let's say. So at each node of the tree, you apply this function called Plotkin. I will come into what it is later, but all you need to know is there's a fixed function that you apply at each node, and at the output, you get the code word. So this is how the encoding for both Reed-Muller and Polar codes look like. And the only difference between these two codes is where you put these frozen leaves. So that's the only one distinction between Reed-Muller and Polar. And apart from that, these two codes have the same computational graph, encoding or encoding tree, which is called the Plotkin tree. And the Kronecker operation comes because this recursive computation can be viewed as a Kronecker operation, right? You take the classical polar matrix and it's just a complete binary. This recursive function can be thought of as a Kronecker product. And so that's what the KO comes from. So this is the structure that ties them together. And so there's a lot of common structure to this, and it's taking a step back, it feels somewhat like, I don't know if it's surprising or it's a bit too good to be true that, you know, like among all the codes that are known out there, and these two codes are known to be proven to achieve capacity, and we know that both are very good, and there's a lot of common structure that ties together. So that definitely hints that there could be something deeper going on, right? It cannot just be that, I don't know, just two good codes that turned out to be both in the same family that turned out to be so good. There could be something much deeper at play, and that's actually the starting point for this project. Is there a way?
I'm just going to interrupt. RM is not known to achieve capacity, right?
Sorry?
Reed-Muller codes are not known, at least like they're believed but not proven to achieve capacity. Like
they were proven last November.
Okay, then I don't know that result. Okay.
Very recently by Pfister and his students. Sorry, I should know the name, but yeah,
Kumar Pfister, Kronecker, Modeli, Sasolu,
No, that was for the Eraser channel.
No, but it was also, the extension to all binary memoryless channels.
This is only two others, if I remember.
Okay, maybe Yeah, but I don't know if Shayantan is confused because they proved it for constant rate Reed-Muller codes. I mean, where the rate is like bounded away from 0 and
Is Reed-Muller and Polar achieve capacity from the channel?
yeah.
No, sorry.
Proven recently.
No, what are the channels for which Reed-Muller codes achieve capacity? I mean, I don't know this.
Binary containers channels. BEC, BSC.
Oh, okay.
Yeah.
Oh, so what's the reference for this?
Fister,
If you just go to Henry Fister's page, you will find it.
I think November 26 or something, 2020.
Okay, okay. Thank you. Thank you.
So yeah, coming back, as I was saying, so there's these two codes that are known to be proven to achieve capacity. It's a lot of structures, so there could be something deeper at play. And is there a way we can discover even much richer class of codes in this family? And that's exactly what we find through our work. Is that we give a class of codes or codes called KO codes that encompass and fully generalize the existing Reed-Muller and that's exactly our main contribution. And for the rest of the talk, I will talk about what these KO codes are and how we design them and how do we broaden this space. So in case you have any questions. Okay, good. So this is a brief overview of what KO codes are. As I was saying, these are new class of codes that are discovered or learned by neural networks. And these codes outperform the classical both Reed-Muller and Polar in certain regimes. And I will show in the next few slides how. And module all of this, like from a scientific point of view, they exhibit like many interesting properties that we didn't expect or enforce. Because the only thing that we are doing is end-to-end loss function learning. That's all we are doing, but in the end, they turn out to learn some fascinating properties. And just like slightly tangential, this is not just restricted to this. Even in the case of like game playing and all, they observed like there like some, especially in the context of chess and all, right? There come some game playing algorithm that they have never seen, sort of strategies or moves they have never seen. That kind of things people have observed, like they're able to discover something completely out of the box. And so this in some sense feels like an instantiation of that observation in this specific domain. So that's actually, to me, that's like one of the most exciting thing about this is like how did it learn some interesting property. The property I will touch upon in the end, what that properties it learns. But this is a brief overview of what KO codes are. So next I will talk about what exactly these codes are. Okay, so again, coming back, this is the encoding tree I said as before, right? The Kronecker operation. So for both Reed-Muller and Polar, you have this complete binary tree. At the leaves, some message bits, frozen leaves, there's a mapping, and in the end you get a code word. So the only unknown component in this is this function, right? The Plotkin, and which actually is the crux of both these codes, is this Plotkin transformation. And this is also known by the name of Polar transform in the context of Polar code. They're both are the same. And so what exactly is this Plotkin mapping? So the mapping is quite simple and elegant. So suppose you have two binary vectors, let's say, I don't know, some length 10 or something, both are binary. So the mapping is the following. There's a V and U. So it concatenates U with U XOR V. So this is the coordinate by the operation, right? Just binary block. So the output is of double the length, right? It's just doubling, and this is your output. So you can see some sort of asymmetry going on here, right? Both V and U are not being treated equally in the output. U almost gets a pass twice, and V is like being corrupted in the presence of U. So this this is how like the notion of polarization comes into picture. If you do it smartly enough, in the full tree, you get a full polarization. But this is the starting point of how the notion of polarization comes. But yeah, anyway, coming back, as you can see, this is the classical Plotkin mapping. And so the key takeaway here is that this is a strictly Boolean operation, right? Yeah, like the inputs are both are binary and the output is also binary, and it's a linear operation in the binary space. So you can write it as a linear matrix 1 0 0 1 0 1 1. Yeah. So the both linear and binary. So again, coming back to the point that if you were to broaden the space and you want to discover much more broader class of codes, what can you do here? The natural idea is that you generalize both the inputs. Like say now they're not constrained to be binary anymore. Let's say they live in the Euclidean space. They are any real vectors, and the output function is some nonlinear function. Okay, that fully generalizes my Plotkin mapping. And this is what we call the KO building block or KO neural network that I'm parametrically denoting by the function G. Okay. And okay, this might be a good time. So in case, okay, this is like the crux of the entire project or the work is how do you parameterize G? That's basically the heart of it. That basically determines what your code is, like what class of codes you are learning. So this is where the neural augmentation principle comes into play. Can the audience see this?
Probably not.
No. Sorry. So this is where the neural augmentation principle comes into picture. So here Plotkin is, I wrote it as binary, but think of it as plus minus ones. Okay. So if U and V are both in plus minus one, the Plotkin map, I can write it as U and V is U comma U dot V, right? XOR is just nothing but a binary multiplication if both are plus minus one. So this is how my Plotkin mapping can be viewed. Now coming to the KO neural networks, right? So how do I parameterize this? One blind by just use like a fully connected neural network. One can do that, and we did that. In the end, it will learn something like a repetition code. It won't learn anything meaningful. Even on top of using this much structure, it won't learn it. So the one single idea that made all the difference is neural augmentation. So what I mean by neural augmentation in this case is the following. So G of UV, right? So what we do here, actually we literally add Plotkin of UV, okay, which is like this, right? U comma U dot V. Just I'm writing here. Plus 0 comma some G tilde of U comma V. Basically, I'm adding the neural component to the Plotkin mapping. This is how I parameterize my G.
And how is G defined?
So G tilde is a function from R2 to R. Okay. I mean, all these functions apply on vectors, just you apply coordinate. Right?
So this Plotkin of UV is U real or is it a vector?
So you use the real way. In this case, it's plus minus one, but here we just in the leaves it's plus minus one, but once you go one step above, they are all real values. So these are all
is it R to the N or is it R? Because there you written U and V in R to the N, but there you written a dot product like
You do
coordinate. In this case, it's a Hadamard. Okay, let me know. That's what. Everything is coordinate wise. So
I'm a little confused with this. Okay, so there's one part where in order to define the code, you need to say what these building blocks are, and the building blocks are instead of the standard Plotkin, you're going to replace it with this.
This G.
There is a second component which is trying to figure out what the frozen bits are.
Okay, it's a good question, but in this we are not touching the frozen bit question. We are fixing the frozen bit. Let's say Reed-Muller code had certain phrasing pattern.
Okay.
We will live with that.
Okay.
Polar code had some phrasing pattern. We will live with that.
Okay.
In the end, I will comment about how we can change it. But for this, we are not touching the frozen pattern. We are fixing the frozen pattern, and we are only tinkering with the tree structure. So not even tree structure.
Just to understand, once you choose a suitably parameterized G tilde, you are now going to ask what sort of G tilde will minimize that loss function that you are interested in.
Exactly. It's basically you write the loss function, and the loss function is a function of the parameters G tilde, and you minimize with respect. So far, because there's a decoding aspect, but so far that's the.
Sorry, I think I disconnected when RP was asking that question, but I had the exact same question. You said that you're not addressing the position of the frozen pip
Right.
question, right?
Yes,
So
yes,
you're
yeah.
assuming that is given to you by advice or something.
Right, for Reed-Muller codes, we know the rule. For Polar,
Right.
for Reed-Muller codes, there's a specific rule, right? You choose according to the Hamming
Yes.
weight of the bits.
Yes.
And so we are not changing that frozen bit order. I will fix the order, and on top of that, I will use the same tree. I mean, tree structure is binary tree. I'm only changing the functionalities inside the tree.
Okay.
That's all I'm doing. And how I'm changing the functionalities is this equation. I said I'm replacing it by the G, but the G is parameterized as Plotkin, plus this is like literally mathematical addition, plus some first component I'm not changing, I'm keeping it U1, there's no need. 0, comma, the neural component action is happening in the second component.
So if we need GTD to be identity function, we know that we are going to get a good code. That's
You mean 0, like GTD is 0.
GTD is
0, you already get a good code. Right, true. In some sense, you are building on top of something good. That's where the pixel.
So you want to, build this one.
Yeah.
This line.
So it's true that in principle, a neural network can learn this function. But so that's what happened when we did not have this, when we dropped this and we had this U and G tilde U, it learns something worse than repetition. It learns actually repetition code. It could, I don't know what's the reason, but few people have alluded that it could be because related to the fact that learning multiplication is hard. Probably you might know much better than me in the sense of like representing a mathematical that someone alluded to, that could be true. I can't comment upon it, but that could be one of the reasons. But at least in our case, if we did not have this and asked it to learn it, it didn't work out. Only if we showed this and on top of that added a neural network, it worked. So that's like a heavy, you need some very good inductive bias to make it work.
You're doing coding and modulation. You're learning both together, right?
Right,
It is real numbers finally.
Right.
So it seems like a little bit unfair to the binary code. There, the modulation part is fixed beforehand, but because there nobody was learning the modulation part. So what you have is a coded modulation,
Right.
as opposed to. I mean,
They're not doing them separately, basically. This
right. So it could be that the gains are coming from doing that together better, right? Rather than.
Okay, this also we did an experiment to like allowing the outputs of the Reed-Muller code to be like not binary but real valued. Basically, there's a power constraint by the way.
Yes.
In the end, there's a power constraint even on our code words because if you can blow up the power, it can be arbitrarily good. But on top of that, like the alphabet for them is binary. But what we did is like we allowed them to be strictly real, but you still have the code style. Like after the output of a Reed-Muller code, we scale them arbitrarily so that they can be any real value. Still in like some hypercube only because binary or multiplying, so it would be like a rectangle. And these, whereas ours lie on a sphere. These are not real valued; they can be anywhere. Even in that case, they are not as good as this. I will show that plot.
The rectangle. No. So, is there a way to? I guess that's what you were trying earlier. Restricting yourself still to binary. But
you mean for the comparison?
Yeah, for the comparison.
Okay. Oh, I will show the plot. Okay, I will first show the plots with the binary, and then I will also show where it's not restricted to be binary. But where you can allow you can scale each coordinate as much as you want. Even that also I will show. That I agree that may not fully address all the modulation schemes that you can do. I only recently got to know something called shaping.
So we know that the square shape is a bad idea. When you are constrained, you want to make it look this way. So, so it seems what you have is a coded modulation scheme. Which so you learn about, so there's no separate learn the code then
we want to get rid of it. That's like one of the reasons.
So of course, that's the right thing to do. But just for the purposes of comparison, would it make sense to learn a code, fix the modulation part as they would in a I mean, when somebody is using a Reed-Muller
Right.
or Polar for AWGN.
Right. I think, okay. I think we tried with several modulation, but I don't think you get these gains without modulation schemes, if I'm not wrong. But I have to check again.
The arbitrary is the real numbers, right?
Sorry?
Is it practical?
Sorry?
So the code that you are getting without this modulation, so basically you are getting sending arbitrary real numbers. So
Arbitrary.
But is it possible to implement this stuff?
So there are two angles to it. In the end, you just send real waveforms, right? In the just like in that sense, we are just
And digital, the way we actually these things work, actually work. I mean, is it possible?
So that's the other aspect is how do you get it into the circuit? That's like it's not fully clear. Like these are like you can quantize and stuff. That I will briefly touch upon compression aspect later. How much time do you have?
Yeah, it's not out of time, but maybe 5-10 minutes.
Okay.
Yeah, 5 minutes. Yeah, sorry.
Okay, then
Maybe throwing you down.
okay, so it's okay. I mean, I think that this you got. So this is the how we parameterize and the augmentation comes into play. And this is just the one building block. And for the tree, we have to do it. We do it this way. For each depth, we use a different function basically. Ideally, you can use different function for each node, but they're just like making life harder. So what we do is that each depth we use the same function for this depth G2, G1. This is how the encoder looks like. And of course, every encoder needs a matching decoder. So in this case, we rely on the classical successive cancellation principle, which is that again, look at the Plotkin mapping. You have U and V, you get U and XOR. Suppose you send this output across a noisy channel and you receive the LLR of log likelihood ratio, the corrected code, both are equivalent. Now your goal is to decode both U and V. How do you do it? There could be many ways. The principle, what successive cancellation principle tells is first decode V. The idea is very simple. You have U and U XOR V, right? So Boolean wise, if you XOR both of them, you get V. So the idea is if you use a soft information from these two, you can get soft information for V. That is done by this function called log sum exponential. That's a standard function. Now suppose you know V. Okay, let's say V is 0. You want to decode U. The idea is again simple. You just add the LLR, right? Because you observe U twice. Someone tells you U and someone tells you V and you fix it. You just need to add the LLRs and you get U. That's the addition function. So this is the basic idea behind successive cancellation principle. So in the same spirit, our even KO decoder looks similar. You receive something like the outputs like, okay, this is slight abuse of notation. This is U and G of U. You can think of this G tilde or whatever. And so for the left branch, you need to some functionality for which we call F1. And once you have the output, you send it back and you get something F2. First you decode V, then you next decode V. And you have left and right. And putting it together, you have this decoder. So this is done in a recursive. This is depth first search. First you decode this, but to decode this, you get here and you go back like this depth first search. And of course, at the frozen list, you don't have to decode because you already know. And this is how the decoder looks like. Once you implement the algorithm, in the end you estimate the soft probabilities basically. And this is how the decoder looks like. And put together everything. Encoder you start at 1, 0, we encode them, you get a channel, you get a noisy code word, and you decode them. And in the end you get the probabilities for individual bits. And the main takeaway is that this entire pipeline is fully differentiable.
The channel, so to put a model.
So channel is just a Gaussian channel.
So yes, sorry, everything is there.
So y is x plus noisy code word is code word plus Gaussian, so it's additive, so it's fully differentiable. So with the parameters are in G's and F's. Yeah. So with respect to and from here up until here, everything is just any path you can take, it's all fully differentiable. So this is the encoder and decoder put together. So abstracting this stuff out, coming back, this is how the KO encoder looks like here, and this is how the KO decoder looks like. And yeah, so you are given the architectures. Now you write a loss function, work loss function, or you can think of MSC loss, which is easier. And just that's it. You try with respect to the parameters. Joint is a joint optimization. You parameterize both of them. And so far, whatever I presented is actually only 10% of the project and 10% of the hard work. 90% is in training them. Which of course, like I won't be able to go into all the tricks, but one main trick that I told you is this augmentation. If you don't use it, we didn't learn anything. This is the one trick that made all the difference for this project.
And what was K? So what was the depth of those trees?
So here, for the purpose of the talk, I showed the complete binary tree. But if you actually look at any Reed-Muller tree, it's like a chain, but the left leaf is like frozen thing. Like the depth is like 7 or 8, let's say, but it's like a chain vertically chain.
So the block length is 8
256. So it blows twice every year. It's not a complete, but it looks good for the talk, but like for the actual tree, it's not complete binary. That's one of the.
How many parameters were there?
So very good question. So this G tilde is just a 3-layered neural network. Fully connected, and each is like 64 there. So each of them is not that complicated, but just the fact that each of them sit on top of one another, that makes it training a bit challenging.
So 64 square into 3 into 256.
That's roughly the 8 into 8.
So what is the advantage that you get by just putting gender equal to 0?
Sorry?
If I just say that gender equal to 0, so what is the advantage that you get?
Nothing. You're stuck at the same code you started with.
Yeah, no, I mean, what in terms of performance? In terms of the performance of the raw Polar code, let's say, what is the performance gain that you get with this?
Okay, I will get the next slide. So let's say, you found a grad student and someone trained it for you, and
how long does it take to train? I mean, is it a lot of time?
It's training wise, it's not that heavy, but figuring out the ideas to train it, that's the hardest part. It trains in less than a day on like normal 4 GPU. I'm not talking Google GPUs. My like lab GPU, like 4 GPUs, it trains.
And for like 256 blocking?
Yeah, it trains in less than a day, or maybe 1 or 2 days at most. That's just to like polishing the results, but it's not that computationally intensive in that, like say, but figuring out what works and what doesn't work, that's the time taken.
You fix the rate and then you choose the noise to.
Okay.
I mean, you have to give good training examples.
So that I will show in the plot. What's the you need to choose channel. You can AWGN, you can only channel.
Yeah. So SNR you train with different things.
Okay. So that I will just one more slide. I will get there. That's also very important. What SNR you're training at. In some sense, that determines what set of examples your encoder and decoder are looking at. So for now, like someone, as I was saying, someone trained it for you, and you have the encoder and decoder. Now you're testing how good it is. So baselines. One is I will use the Beer SNR curve, reliability curve. The other is I'll also talk about the complexity as you're mentioning in terms of operations. The baseline. So again, touching upon, I'm using an existing code structure. So I will compare, for example, Reed-Muller, I will take the skeleton and I will compare with the corresponding KO. For the Polar, I will take same philosophy again. So 2 setups. One is I will test it on both the same channel. AWGN channel, I trained it on, I will test on the same channel. And then I will do the other setting of robustness. I train it on AWGN channel, but I will test it on other channels to see how robust my codes are with variation channels. Because in the practice, that's where actually deep learning can play a role in practices with regards to robustness. Because none of the real channels are AWGN, right? So in those cases, how good your codes are. So that's where actually the real power lies for these codes, not on AWGN.
So you're taking the frozen beats just prescribed by the Polar codes, right?
Yeah.
So you're not learning the frozen beats.
No, in this project we are not learning.
Is it possible to learn?
Yeah, definitely. That is again, if someone can do it, that I would consider that it would be a fundamental contribution. It's a very hard. We tried, but I will talk in the end why it's a very hard problem.
It is not convex, right? It is not convex problem.
It's combinatorial. That's
Combinatorial.
the main reason. It's very hard. We tried. For small block lengths, it learns, but afterwards it's just a nightmare. But if somehow someone can figure it out, then it will be fascinating if someone can do it. Just coming back to the results for the AWGN, I will take the AWGN channel, train it, and test it. So this is how the results look like. So this is a blue curve is the Reed-Muller code. So this is the code. K is 46, block length is 512, so tree depth is 9, and the red code is the corresponding KO code. So whatever the corresponding. So here we see like a lot of gain over the classical Reed-Muller codes. And so as you are mentioning, what's the SNR we choose? So thumb rule. So here actually, this entire curve is of a single code. We trained the code. Okay, I think we trained it The 2 points. One, the thumb rule is generally choose an SNR where the bit error rate is between 10 to the -1 and 10 to the -2. So that's the thumb rule for most of this training. Is bit error rate should not be too high because then you see very few errors. It should not be too low because then it's just noisy. So you need to find some sweet spot. And what's empirically, this is something that works best is somewhere between 10 to the -1 and 10 to the -2. So that's the general thumb rule. What happened for us is if we did that, the curve was good up until this point, but after that we had to use a different SNR to try. That code was not uniformly good. Luckily, in this case, we found that something we trained at this high SNR, it's uniformly good across all the SNRs.
So how did you choose your training set?
Training set is like very
Uniform.
Yeah, random message split. There's no like a Boolean hypercube. The input distribution is uniform on Boolean hypercube.
How many training examples?
So we train it on batches. So large batch sizes help basically. So in this case, I think if I'm not wrong, we use 100K. If I'm not wrong, 100K or I think 100K was the batch size or 10K. I forgot. One batch like one pass it on a single batch. And the entire gradient you get is on the entire 10K samples. I think 100K. I think it's 100K. You need large batches, otherwise
It's too slow.
so it's
Too slow.
it doesn't learn. It's possibly because it's not seeing enough errors to get some gradient.
It needs noisy.
You need large batch sizes. SNR is the right. You need to choose good SNR, and yeah, some those are the main tricks. In this case, this is just one single code, uniformly good across all the SNRs. So it may not happen always. Sometimes you might need 1 to SNRs, but which is also okay. So this is for block length fight. Well, the rates are still low. We are targeting very low.
These are like multiple simulations, right?
Yeah, this is
So this is not trained, so this is tested.
this is tested. Someone fixing. We are fixing the code. Like someone trained it for you, and you are fixing the codes. You are just testing it.
Uniformly.
Yeah. Of course, this is not a representative of the entire. We cannot because there is no way we can simulate 2 to the 46 messages.
Right.
This is a nonlinear code. So there's, but I think we ran several trials and the curves don't change. So that's like some indication that. But of course, it's no theoretical guarantee that this is the actual performance of the code because there's no way we can simulate the entire message. This is for block length 512, and we observe a similar pattern for 256. Just that the gap slightly wider. Shrinks. Just that if you have longer block length, there's much more room for improvement. I think. And that's the philosophy with Reed. So the observation with Reed-Muller and Polar as well. We observe a similar pattern. But one thing interesting happens is so Polar. I mean, no, you know that Polar at finite block lengths is not that good. For example, if the Polar with successive cancellation is blue curve, and you can do Polar with map. In this case, the green curve. So there's of course a quite good gap. And what happens with KO codes is that the decoder it has, and also if you can compute map in this case, because the dimension is 7, so you can do map very easily. It turns out that the decoder almost has like a map-like properties, though we did not try that. But we didn't say anything apart from the loss function. And in some ways, it learns some nice nearest neighbor-like properties, right? That's how the map decoding looks like in AWGN. It's just a nearest neighbor matching. So it learns, despite a lot of structure, it is learning some interesting properties. That's the something non-trivial about this. And yeah, this is just under AWGN, and again under fading, you observe similar thing. You take a code that's trained on AWGN, it works on fading, and this is not actually restricted to this. People have observed like robustness of deep learning methods for various scenarios if you can train it properly in one setting. Like in this case, AWGN is known to be like theoretically hard for, is a benchmark for several reasons, right? Theoretically and practically, and in the, it turns out that it's good also on fading channel. And of course, the catch here is that fading is not that different either from AWGN because there's some Gaussianity aspect. But if you were to use some non-Markovian, something like non-Markovian, some other channels with some state, it's not entirely clear how robust these codes are. That's also interesting. But at the end of the day, you can take these codes on AWGN and you can train on those channels. So that's always there.
Deletion channels. The deletion channels.
If it's a non-differentiable channel, so it's not even BSC. That's why I did not show because it's not clear how you train it on a BSC. And once it becomes real valued, what do you mean by BSC is also not. There is no notion of BSC, right? For us. So So that's how like the BRSNR curves looks like. And complexity wise, since we are using the same tree for both the codes, it's O of n log n because nothing changes apart from the function. So algorithmic complexity is the same, but if you count the number of operations, there's a neural network sitting there, right? So if you count the basic operations, which is multiplication and addition, KO codes is almost like 50x Reed-Muller codes. So there's a lot of improvement on the cutting down on the complexity wise. We did some initial experiments along this where I told you that this is a 3-layer neural network with 64. What we did is we replaced with 1 layer and 4 neurons. If we did that, what we get is something we call tiny KO. So it has the operations almost comparable in the same order as Reed-Muller codes, but it won't lose the performance as much. So definitely there's a much more room to play this compression game, compression and performance game, which are not the focus for us. For us, the main focus is does there exist a better code out there? So that was the main focus. And so this is a complexity good, but okay. So far I talked about why these are good and so on, blah blah. But the main takeaway is, you might wonder, right? At the beginning, I said like, what's the main purpose behind why you're discovering codes? And in this case, we saw these codes are good, but then it makes you wonder what makes them good, right? Like from a scientific point of view. So this is what we found is something very surprising is that they exhibit some random Gaussian-like properties, which is something completely unexpected because there's a lot of structure to the encoding, right? We are using the tree structure, the encoding and decoding. But the encoder somehow resembles Gaussian, random Gaussian. What I mean by that is the following. So here, what we did is we plotted the pairwise distance between the code words. So on the blue checkered one is the Reed-Muller code. It's the staggered one. That's the you take the code book and you compute the pairwise distance. This is a histogram basically. So the orange curve is a random Gaussian code book for the same parameters. They're all of the same parameters. And surprisingly, we found that the histograms for KO codes and random Gaussian, they almost like exactly match.
So what was the initialization for this G tilde network?
G tilde is almost close to 0 in the beginning. It's like random Gaussian with very small variance, I think 0.01 or so in the beginning, it's almost like a polar code or Reed-Muller code. Once you train, then it learns something non-trivial. So, but the surprising factor is but this Gaussianity kicks in at the code word level basically. It's like the code words lie on a the unit hypersphere, right? Because the power constraint is the norm square is n or whatever. This is our power constraint. So they lie on some unit hypercube. And we are plotting the pairwise distance basically for the code word. That's the histogram. So that's where Gaussianity kicks in. So it's not clear where it learned that or how it Gaussianity slipped into this.
Does it happen if you change the channel to relay or something?
If we changed it to relay, okay, we did. I think we changed the bursty channel. We tried where we changed the bursty probability and the sigma just so that you have a family from Gaussian to. Basically, we have a way of getting away from Gaussian to something non-Gaussian, maybe slightly. There also, I think we observed a similar pattern. It resembles somewhat like Gaussian, if I'm not wrong. I have to check. I have the plot somewhere.
Is it a consequence of like strong some concentration? Because I mean, to really see whether it's Gaussian or not, you want to look at the tail, right? Like really, like, I mean, of course, there's no tail for this one because of the 0, but that is where I mean, in the sense that even if we take binomial random variables, they look like Gaussian, but not really. They are more like Poisson. So that thing is something like that happening. That is because it's so concentrated. The original Reed-Muller profile is so concentrated at 32.
Right.
Small perturbations around it because they're just small. They will have this. I mean, so what does the Gaussian thing mean? It has this x squared, like so that comes across from many other. So I'm just wondering if there's something not about KO code, but just about the fact that the Reed-Muller code distances are very concentrated, and you expect and the Gaussian code also is very concentrated just because we're just choosing. And anything else that is only going to make small perturbations to Reed-Muller will have.
I see.
Profile like this.
I see. We'll check that. Yeah, that.
So how much does the distance change? I mean, so if you're starting with polar codes, right?
This is like I think Reed-Muller
Reed-Muller, let's say. And so you have the initial distance distribution. So even after training or when you actually get the code, it looks the same, right?
Initially, it's Reed-Muller.
Initially, it's Reed-Muller. Then after training, you get this. It's almost the same. The distance distribution.
It's almost like Gaussian now.
Yeah, both of them are Gaussian, right?
I mean, Reed-Muller is not Gaussian, right? Like it's like very distinctly staggered, checkered thing. So.
Okay. Okay. I mean, okay, you're talking about the district, but I'm saying when it is actually picking, it's in the middle.
Somehow I think it's the peak and the thing it's related to the power constraint. I think if I'm not wrong. I think average pairwise distance on this hypercube, the sphere or something. I think something related to that. I think. Okay. Yeah. So this is like what I was alluding to in the beginning is like they learned some interesting properties that we didn't impose or like something unexpected. And I think like it's wide open why they exhibit this kind of thing theoretically understanding or showing something about our codes. And so that like there's like some immediate directions. Okay. The one important direction is as I was saying before, like how do you learn the frozen bits? This is not we didn't touch upon this. There are some works that try to do this, but not like not at this level of like learning a code together with this. They do it with reinforcement learning based tricks. But it's a very hard problem because we spent like 3 months and we gave up after that, trying to learn the frozen bits in this regime of Reed-Muller and Polar. But there were a new class of codes called pack codes, again by Erican, that they were actually beating the heck out of every other code. They achieved like the fundamental dispersion bound. So that's where we put a pause on this and we were looking at there. The frozen thing is a bit different there. They use a polar code, but there's no frozen bits anymore. They use a rate 1 convolutional code and those codes are like much better than these codes, and that's also an interesting direction. So these are like some immediate future directions, but like long-term directions, as we were discussing before, also like. So if you think about it, like our work uses this recursive tree structure, and existing some other works they use several other tree structures. But if someone were to give you the freedom, of course we have the freedom of can you discover completely new structure altogether? How do you do it? Like can you? It's a bit vague also. It's not clear what because by structure you mean you are asking for something, right? Like structure means some property and all, like what kind of properties you desire, and how do you formulate it mathematically also is not clear to me. But I feel like that could be like some fundamental contribution if someone can come up with a way of discovering new structures altogether. And this work, all the results I show like clearly empirical in nature, but definitely as you saw, there are many avenues where there's a lot of good scope for do theory, like understanding the class of codes it's learning, or just from a theory point of view, understanding the loss landscape, training, generalization, and all these things. So it's like room is like wide open, like this, just starting. And this the entire talk I only focused on point to point, but if you that's just like a minuscule of the entire communication operations, right? Like there are like lots of complicated net interference channel, relay channel, network coding, and data storage. Like there are many wide applications, and there are also already works in the coded computing regime trying to learn codes by I think several groups. And so these are like many interesting directions. If anyone is interested, I'm happy to chat. And I would like to thank all my collaborators, without whom this wouldn't have been possible. And thank you. GTIL, it's just like a input is 2 and this is 3-layered.
And you have a lot of GTIL that kind of
GTIL is basically the tree.
The plot in GTIL.
Log n. I mean, Block length doubles at each node, so you have log n depth.
Okay. So over here, like, so this like each neural network is giving you some parameters which are and they are all adding up, right? So did you try to optimize over the number of parameters in this sense? Like, I mean, maybe you are getting some polynomial in the end, right? Which is encoder, some nonlinear map, which is encoding map and a nonlinear decoding map. So what level of nonlinearity is required to get the better rate curve that you are getting? Like, maybe the code you are learning is like highly nonlinear, but maybe that's not really required. You might require only a slight amount of nonlinearity to actually get that.
So it could be true that in the end, I forgot about the encoding side, but the decoding side, I looked at what it's learning and all. There, because for example, if you fix the Reed-Muller code, and if you train the decoder, it's supposed to mimic the successive cancellation actually. It cannot learn something better given it's like a local minimum. Like if you fix the encoder and you train the decoder, it will learn successive cancellation. If you fix the decoder and you train the encoder, it will learn the Reed-Muller. So what we did is we fix the encoder and you train the decoder. There it's matching successive cancellation, but it won't. But it will learn something interesting. It will learn some formulas so that in the end it will still match successive cancellation. So what I observed with this neural network is you're training it as fixed SNR, so it's learning some formulas based on that SNR. But the thing is, you observed it after training it, but I don't know how do you reimpose it even in the beginning itself, as in like if this is the structure all you need, because we don't know if this just suffices or not, right? Like the kind of, because it's something is a byproduct of our training.
No, like, I'm wondering like if you want to generalize Reed-Muller codes or any other existing codes, you might be getting something very arbitrary nonlinear thing out of neural network, which might hit that thing at some corners, but you don't really know like how close it is. Like, I mean, if it is the most like more succinct or in some way, then there's more hope of like trying to understand some structure out of it. If it is there are so many parameters, it's really difficult to get your head around and try to understand some structure.
I agree, but we may not look at the parameter by space. We can look at the functionals because this function is still a bivariate function.
Yeah, okay.
So that can give us a lens like handle of how do you.
Okay, maybe some approximation.
Yeah, that could be possible. That's possible because this we can simulate, right? Or we can plot.
And another thing that you mentioned was some Gaussian codes. So I'm not aware of what Gaussian codes are, but like
random Gaussian code. IID random.
Okay, what is the meaning of that?
Suppose you have like block.
And that's just existential. Oh, you just pick and with like whatever you get, you just use.
It's just like random Gaussian code. Like in Shannon's proof, we use like random Gaussian code book. It's exactly that.
Yes,
I mean, we can simulate it also. Like so block length 512. So 512 entries are random Gaussian. That's it. With the power constraint. It's basically it's 512 dimensional random Gaussian code word. That's the random Gaussian. And we just plot for the random Gaussian code book, we compute the average pair distance. And that's the orange curve. Of course, it's Monte Carlo simulation because you cannot simulate that.
What was the decoder that was giving this thing?
I mean, it was trained with some joint decoder, but this we are only looking at the code book. So we didn't. Decoder also learns interesting. In that case, that's the experiment. We fix the encoder and we try the decoder, and it learns some formulas. Actually, very interesting. So that in the end, it matches successive cancellation, but it learns some nice formulas. The neural networks learn some formulas based on SNR. So that in the end, it still matches the successive cancellation values in terms of time.
Also, do you have any insight on what these deltas look like maybe after plotting them?
I should have done it, but we're trying to analyze this. I will get back to you soon. Like this is something we know like to do for a long time. What happened is the following: we were trying. So this curve we got and we're trying to understand that we realized that backwards came. I mean, it came long back in 2019, but we realized that we might as well target like that's a much bigger price. So their answer like very fascinating. Like they beat actually all these codes. They're better than Polar. Reed-Muller, Reed-Muller doesn't have like efficient decoders. That's like even backcodes that's the problem. But if you just look at from a code point of view, backcode is much better than Polar code at finite block lengths basically. And they achieve like this fundamental PPV bond, like the dispersion bond. The best bit error rate you can get out of any code on a AWGN channel. So they achieve that bond. And Arikan gave that in his Shannon lecture, I think, in 2019. So these are like, someone is interested, I think. I feel those are the codes one focus more on.
So once you learn these things, suppose you really want to implement them, then it's just a simple map, right? It's just a lookup table you will be.
This is not exactly lookup table because it's a. For this block.
Because it's a huge, the size is huge, the size of it is.
Yeah, the block code is just.
So you would want to have some algorithm.
Yeah, in chips is always like a implement in chips.
So over there, some questions of algorithmic complexity.
Yeah, how do you fit the neural network? But that's like a wider.
Okay, that's like once you have this plot, then you would want to fit them in some nice way so that you can. Once you have your GT function.
Yeah, we fit the neural network onto the chip directly.
Oh.
Generally, you have Boolean gates to implement plot kill, right? It's binary of u dot v. Instead of that, now we have a neural network bound onto the chip. How do you do it? That's of course not.
Okay, you would have fixed parameters, some fixed parameters.
Everything is fixed.
So it's just yeah.
That's why robustness is important because once you bound them on the chip, right, the channel might vary. Right? Like what channel conditions you operate that might vary according to application. So you desire the one code that you have to be good under several various regimes. Of course, you would want to, if the flexibility retrain, but again, that's an overhead, right? So it would be, that's why robustness is always desirable. Like you have one code bound onto your chip, you can use it over any setting you want, let's see. And that's one area where I think there's a lot of scope for sure for this data-driven codes, are like better than like human constructed codes. They are like people know that even if you deviate from AWGN, many of these decoders fail, like classical decoders they fail. They're not that good. That's where I think these deep learning methods can play a much bigger role. Like if they're robust to the variations in the channel and these kind of things. Yeah.
Okay, very good. Let's thank Ashok.